gain the knowledge about synthesis and study of applications of the nanomaterials. Rajkumar Garu have reported a bunch of research papers and patents on nanomaterial research. I am very much confident he will justify today's topic. Thank you. Now I request Adjunct Associate Professor Rajni Madam Garu to say a few words.
Thank you, Madam. The outset, I also welcome Dr. B. Rajkumar Garu to deliver his lecture on nanocellulose, a sustainable replacement for plastics and more. As everybody knows, nowadays the nano research is being promoted a lot. And similarly, everyone knows that plastic is how much harmful to the environment as well as for human beings and the animals also. Recently, floods we have reported. Floods were reported at Kurnool very recently. So all these, the present generation, I think they'll be knowing the hazardous effects of plastics, which are not biodegradable. So from then onwards, people are behind knowing ways and means of the sustainable plastic, which is biodegradable also, whereby we can avoid such type of difficulties that is usually in oceans also. In Bombay, recently we have noticed that NGO organization has collected all plastic waste from the surroundings of oceans, and they were doing a lot of help to the human beings, whereby if we throw the plastics into the oceans, the marine animals, it was becoming hazardous to the marine animals also. Therefore, it is not so simple. It is very hazardous, both for the life as well as the water animals also and the environment. Therefore, I think this is the right time. Our department has gone for such a type of topic for as a webinar we are conducting. I congratulate our department on behalf of Dean Madam also. I congratulate and I thank our Vice Chancellor for giving such a beautiful opportunity for the Department of Chemistry. So not only as I said for environment, for packaging also. Nowadays package industry also has grown a lot because of online marketing. So there also you can use this nanotechnology, and then for repairing tissues also. Sometimes these nanotechnology is very, very useful. That is in medical field and as well as in extractions and petroleum as an alternative to petroleum-based plastics. All these things, I think the resource person, the speaker will be enlightening each and everyone on this topic. I welcome you, sir, on this occasion to deliver your lecture. Thank you. Thank you very much.
Now I request Kotes Rao to introduce the Rajkumar.
Yeah, good morning all. Welcome to today's event. This is a great opportunity to me to introduce today's speaker and my former colleague, Dr. B. Rajkumar. He's completed his MSc in Organic Chemistry from Telangana University and received PhD from Usman University. Currently, he is working as a postdoctoral researcher at Kangwon National University, South Korea. So far, he was published more than 35 publications, research articles in international peer-reviewed journals, and he written 7 book chapters, and he has credited 1 patent. His current research interests included extraction and chemical modification of nanocellulose from ligonucleus cellulose biomasses, preparation of cellulose-based composites with carbon dots and metal nanoparticles and applying them in pollutant removal and biomolecular detection and biomedicines. I welcome you, Rajkumar Garu, for your for today's event. Thank you for your accepting your departmental invitation. Thank you very much. This is your time. Please start your session. Thank you.
Okay. So, good morning, all. Good morning, all. First of all, let me thank you for inviting me on this lecture. So, my today's topic, as I already mentioned, the title you know well, the nanocellulose, a sustainable replacement for plastic, and more. So, just a moment, I'll give you this. Yeah, let me start with. So when you heard about plastic, so generally all have some negative opinion. So the plastic is bad, something like that you will hear. But so is it really bad? So the plastic actually is a wonderful material, but it is having some problems. So in this age, we can call it as a plastic age. So generally we have seen the anthropogenic age, like the development of mankind. If you observe the development of mankind, you can find the ages like Stone Age, Bronze Age, Iron Age, like that. So if you consider our age, this is called the plastic age. So here we are living with plastic. So everything and anything I can say is made up of plastic, from packaging to and the electronic items and the textiles, the clothings, and of course consumer products, and even the car and automobile industry and all. So most of them are made up of plastic. So actually it is a great and wonderful invention. So but later the people find out that most of the plastic is non-biodegradable. So the two biggest problems with the plastic materials are they are non-biodegradable and they're difficult to recycle. That means non-biodegradable means if you leave that plastic in the environment, so the natural microbial things or the natural conditions like pressure, water, moisture, soil, these things cannot degrade the plastic material. So it cannot be broken down. It will remain as litter on the earth surface. So, and the second one, if you want to reuse, so it is not degradable. So we want to collect and reuse for another things, but it is highly difficult to reuse or recycle the plastic. So why it is difficult? I mean, if you reuse or recycle, the cost of recycling is actually higher than the new product. It is very higher than new product, and the new product look pretty good and everything, and the recycled one will have no good properties. So like the properties are not up to the mark. So generally the consumer or other person prefer the new one. So like that, there is a lot of plastic remained on the earth surface. So if you see the statistics, global statistics, so you can observe the huge spiking, like logarithmic trend. So the plastic production got increased a lot with the rapid industrialization and ever increasing demand. So if you take some kind of statistics, here the plastic, this is all the plastic produced. If you consider it as 100%, you find only 30% plastic is still in use. And only a little percent, that is 6% up to, can be recycled. And 8.5% is incinerated. That means like burned off or degraded. But rest, the 55.4, the major percent is discarded on earth surface. So it will be like, cannot be used. Okay. So, and if you see the categories wise, so different industrial wise, you see the major share is packaging. So the 47% is packaging. So whatever you buy, even from the store, like from the vegetables, starting from vegetable, food item, and everything will be packed in a plastic. So this is causing the big problem. So I think you all know about this, but I'm just giving the basic statistics. Okay, so next, let's go to this. So, and where this plastic will get accumulated. So mostly, so the majority of the plastic is accumulated on oceans because everything will be run off, like the drainage and everything will lead to river and ultimately lead to ocean. So everything will be there in ocean, mostly coastal lines. So the big problem with the plastic is it cannot biodegradable, but it will like broken down into small pieces only. So that small pieces is called microplastics. So this is the biggest problem. So this microplastic will remain in like water column, like in the ocean, or in the deep sea. Okay, and you can find this small plastic in the soil or anywhere, and in some animals, even inside the body. And very recent innovation, like recent discovery stated that even in the human blood samples, they found microplastics. That means it can enter our body also. Like the microplastics are most dangerous. Okay, so then that means there is a great need for alternative material. So everyone know this, we need to go for alternative. And where to go? So generally, the well-known alternative materials. So here I am showing a little like well-known alternatives for the single-use plastics. Like if you can replace the plastic with the wood spoon and the paper cups, paper packages, or the cloths or the fiber, like jute fiber, something like bags or cloth bags. So I think most of us know about these things, and some of us are already using these things. But why we are preferring this? Okay, do you have any idea? So why we are preferring? So these are because they are made up of plants or something like plant thing, and they can be biodegradable. They can be degradable very fastly. Okay, that is the first, and they are made up of plants, so we don't have like a petroleum-based problem. Like the plastics, if you see, they are from petroleum-based products. They are non-recyclable. They are non-renewable. So the petroleum resources are non-renewable. Once they got depleted, they are gone. But in the case of these plant-based things, you can raise the plants, cut the plants and harvest them, and then again you can raise them. So like that, they are renewable. So their sources are renewable, and the second thing, they are biodegradable. Okay, this is the most common one. This is a general, like a normal person will look at it like this. But how a researcher or a chemistry student will look at it is, so you have a question, like what it is made up of. So what is the chemical composition for this? So okay, anyone have idea this? So the wood part or the paper, all these paper, cloth, wood, what it is made up of? So that is the cellulose. You heard about this. The cellulose. Cellulose, along with cellulose, lignin and hemicellulose. These are the major things. So actually cellulose is called the basic structural unit of plants. So the strength for the plant is due to the cellulose. So the difference between animal cell and plant cell is the plant cell have cell wall. The cell wall is made up of cellulosic material. Cellulose, hemicellulose, and lignin are strongly bind with each other to make a strong fibers. That fibers will give strength to the plant. Okay. So this, here I'll show you the simplest diagram. So the plant tree, if you cut the wood part and cross-sectional and another sections you see the growth rings and this one. This is a wood block under microscope. Okay, so when the wood is dried, the most of the cytoplasm in the cell will be gone. The moisture part will be gone. Sir.
Rajkumar sir, I
Yes.
think slides are not moving.
Not moving?
Yeah, just scroll it once up and down.
Where is the slide?
Yeah, okay, now okay.
Now okay?
Okay, you can move.
This okay?
Yes. It's
okay.
okay.
I will just show you one more time, simply.
It's okay,
this is, yeah. Okay, so I will slowly run one more time. I mean, overview. So the plastic is used in many industries. So this, you know, and the statistics will be like this. Majority is discarded, so cannot be recycled, and majority in packaging industry. So this packaging industry, every day in our family, like our home, we dump a lot of plastic due to the packaging of biscuits, everything, fruits and everything. We have some plastic package. So, and the plastic will be accumulated in the ocean, coastal areas, inside the water and inside the deep sea, and some soil, and in the blood and inside the body of sea turtle, or sometimes our human body also. So next, the alternatives. So these are the alternatives I explained for plastic. So the regular using wooden spoons or paper bags, cloth bags, jute bags, all these are alternatives, paper cups, whatever you use. So all these are having a chemical composition that is cellulose, lignin, and hemicellulose. Okay, most of them are wood-based products. So if you carefully observe, the alternative material to plastic are all are wood-based products. Okay, so the wood, then what is actually wood composed of? So the wood is composed of like the cell, wood cell will be like cell wall and inside cytoplasm. So if you dry the cell, so the cytoplasm will be gone and the cell wall is the actual rigid structure. Okay, the cell wall rigid structure under the microscope will look like this. Okay, this is outer wall, primary, secondary, and inner cell walls. Okay, from this cell wall, so this cell wall have fibers, fiber structure. So this cell wall fiber is made up of hemicellulose, lignin, and cellulose. So if you further go down to its hierarchy, like further separate the fibrils, if you separate the fibers, you will observe microfibrils. And these microfibrils further observe elementary fibril, a thin nanofiber, nano-sized fiber will be there. So these nano-sized fibers will be bundled with each other and form like hemicellulose, and lignin add some strength to these fibers and finally make a cell wall fiber, which is very strong and tough. And if you look at the chemical nature, so the cellulose is a linear polymer of glucose. So glucose units are linearly polymerized. So there is no side chains, only linear units are there. So, and the D-glucose units. So the D-glucose units are linked with beta-1,4 like glycosidic bond. So you can observe here. So this polymerization of glucose with the loss of water molecule, it will give you a linear chain of cellulose. Okay, this cellulose in the wood, like the wood powder or from the wood part. So the cellulose, if you look at the hierarchical structure, so there will be like the bundles of fibers will be there. And the bundles of fiber, if you go down to the nano level, there will be nanofiber. So this nanofiber will have alternate crystalline amorphous regions. Like the nanofiber is a long one and it is made up of some crystal part followed by amorphous weak fibrils, then crystalline part and amorphous part. It will be alternative. So this kind of long fiber is called cellulose nanofiber or cellulose nanofibrils. And there is another form, this, if you remove this amorphous parts, and there will be only crystalline rod-like structures. So these kind of rod-like structures are called cellulose nanocrystals. So generally from the wood, if you consider, there are two types, cellulose nanofibrils and cellulose nanocrystals. Let's go back to, so this is a typical simple microscopic image of nanofibrils and nanocrystals. So I will explain about these things later. So first jump into the nano. So I think most of the students who are attending here know very little about nano. So I want to give some briefing, some introduction about nano, and then go back to the cellulose nanofiber. Okay. So the first, the nano scale. So the nano word itself says like it is, I think most of you come across this word like milli, centimeter, millimeter, like that, centimole, millimole, micromole, again, nanomoles. So the micro is, you say, 10 power minus 6, and nano is 10 power minus 9. So the nanometer scale is the 10 to the power of minus 9 of meters. Okay, 10 power minus 9 times smaller than a meter. So this is simple. I will show you this little. So if you observe this nanoscale range, so the cells or blood cells or normally bacterial cell or anything, this bacterial and blood cells, this comes under the micrometer range. Okay, so the blood cell is bigger, 100 micrometer, and the bacteria which attacks the cell and go inside this blood cell will be very less, that is somewhat 1 micron, 1 micrometer. And if you go down, the protein inside the cell and the molecules, like bigger molecules, or comes under this nano range. Okay, so the atoms are smaller than this, like whatever the nitrogen, hydrogen, the atoms, the size is very small. Okay, nanoscale. Then the type of nanomaterials. So the types of nanomaterials can be classified into 4 simple categories. So this is just based on the, like their shape, geometry. Okay, based on the geometry, nanomaterials can be classified into 4 types. So the clusters or simple nanoparticles. The clusters, or these are also called as zero-dimensional materials. So these are nano in all dimensions, like they are spherical particles and their diameter will be less than 100 nanometers. Okay, these called nanoclusters or nanoparticles. So then another second category is nanotubes or nanofibers, fibers or rods-like structures. So this means if you look at the fiber-like structure, it is thin and the diameter and its length is very high. So the diameter is thinner and length is very, very higher than diameter. So this is fiber-like structure. So if the fiber diameter is less than 100 nanometer, that kind of fibers are called nanofibers. And another case, depending on the structure, like if it is rod-like structure, and it is called nanorod. If it is long enough, like very long, up to 1 micron, and it can bend like the flexible one, then it is called nanofiber. And some other carbon nanotubes also there. There will be example for you. Next, the films are actually, they are called nanosheet-like structure. sheet-like structure means they are two-dimensional, like a square like the sheet-like structure. So the diameter, like thickness, height, width, and thickness. So these three will be there, but only in 2 dimensions. It will be nano, like either thickness or like thickness and width will be in nanoscale, and the sheet length may be higher or nanoscale. It doesn't matter. So these are considered 2-dimensional and 3-dimensional one. So the 3-dimensional ones are similar to the clusters one. So these are all also nano in all sizes, all dimensions, but the nanoparticles will be smaller and spherical like structure. These will have some certain shapes like nanocubes, like cube-like structure, polygon-like structure, something like that. Okay, this is a basic introduction about nano. So the nano means any material which is less than 100 nanometers in size. Its size should be less than 100 nanometers, and it may be in 1 dimension or also. Like the total size is less than 100 nanometer, the nano clusters are 3D. So only diameter is less, mean 1-dimensional or 2 dimensions, depending on the dimensions. But the ultimate definition for you is the size should be less than 100 nanometers. And yeah, you heard the nano many more times, I think, but why the nanoparticles are very special? So why all say nano? Nano is why different compared to all others? So the biggest statement or simple term I can say, the higher surface to volume ratio. Like the number of particles or atoms or centers present on the surface are very higher than in the core. So this is the simple example for you. So if you see a big particle, this is not nano one, very big one. So the total atoms, suppose 792, and on the surface only 390. That only 50% will be there on the surface of this particle. So if you reduce the size, like if you break this particle into smaller particle, so the particle size will be reduced and the surface atoms will be increased, because the atoms present inside the center will become less number. And if you further reduce this to nanoscale, so the atoms on the surface will be more. So almost it will become 10 total atoms mean 10 on the surface. There is nothing inside the core. All are present on the surface. So this kind of higher surface to volume ratio. So this leads to new properties. So here the surface is suppose 50% and the total volume is somewhat. Like if you decrease the size, its volume will be decreased. Like total volume will be decreased. And at the same time, the number of atoms present on the surface will be more. This kind of higher surface to volume ratio is the reason for its new properties. So what kind of new means? So in case you all know about the gold. So the gold looks like yellow color, right? Gold will be an yellow color, that is in the bulk form, like when you see in the big size one. So if you go to the nano level, if you see the nanoparticles of gold, they look like purple color. So they will appear in purple color. And if you change their size, slightly change their size, they will become blue, purple, blue, and different colors they will exhibit. So that kind of variation in the optical properties. At the same time, there are several variations in the electronic and mechanical, all other properties. So because of this higher surface to volume ratio, they exhibit different properties, novel properties you can call. So because of that, they are considered like more fascinating materials. And here, the next is the preparation methods. So how we can make nanomaterials? Just a moment. Okay. So nanomaterials, how you can make them? So you have some bulk material. So this, we have some gold or metal form, big bulk one. So if you break down to very small particles until the particle size becomes nano. So this kind of breaking down from bulk to nanoparticles is called top-down method. So we are starting from the top and going down to reduce the size. And the second type of method is bottom up. So in the bottom up method, we select the atoms. So if you take a solution like metal ion solution, suppose copper nanoparticle. If you say the copper ion solution, so the copper ion size, atomic size of the copper will be very less. Like when compared to nano, the atomic size will be less. So the copper atoms, if they come close to each other, like atoms come close to each other and bind and form some clusters. So the clusters again slowly aggregate or bind with each other to form nanoparticles. And actually they continues to aggregate and become bulk if you leave it. So, but if you control the size in the nano level, you will get the nanoparticles. So totally two types of methods, top down. So here you cut the bulk material into small particles. And this one requires high energy. You know that cutting down to nano level means you need some mechanical energy or the instruments that give high energy to break down. So the breaking down a metal, just imagine the copper rod. If you want to break down to nanoparticle, small sized particle, you need a lot of energy. So in the second case, bottom up. Here you use copper ion solution or some metal ion solution and slowly control its chemical reaction. Like add some reducing agent to make copper ions to copper atoms. Then the copper atoms slowly start aggregate and you control their size in nano by adding some other reagent, that is capping agent. So it will control the size. Okay, so this is like a wet chemical reaction and it can be easily controlled and easy to operate. This is the most commonly used method for making nanomaterial. Okay, let's come back to the cellulose nanoscale. Okay. Here I will show you the nanoscale. So the wood block, if you look at it, the normal size will be somewhat some small wood piece, 10 centimeter. And if you go down to the cell structure, so the plant cell will be somewhere around 100 micrometers. And the cell wall, so if you look at the cell wall structure, this will be micrometer, cellulose fibrils. So this will be suppose 10 micrometer. And this cell wall structure again have small fibrils. This is individual nanofibrils. And if you look at this fibers, so this is the nanofiber. And if you go to the chemical structure, it will be cellulose chains, individual cellulose chains. So linear chains of cellulose, they are hold with each other. So here there is no, like the cellulose is a linear polysaccharide. Okay. So it is linear polymer of glucose. There is no cross-linking, but the adjacent two chains of cellulose. This is one cellulose chain, another cellulose chain. These two cellulose chains are bind like there is some hydrogen bonding interaction. So if you look at, go back to the chemical structure. Yeah. If you go back to the chemical structure, here you can see the cellulose glucose units, and each unit have hydroxyls. So you can see each glucose unit have 4 hydroxyl groups here, and in the middle one, the glucose unit which is there in the chemical linkage, this have 3 hydroxyl groups, OH, OH, OH here. So these hydroxyl groups are well known for involving in hydrogen bonding. So the 2 glucose units adjacent to each other will involve in hydrogen bonding. So each unit having 3 hydrogen bondings almost. So there will be a polymer, means a long chain and having many more number of glucose units. So there will be a huge number of hydroxyl groups. So there will be a huge number of hydrogen bonding interactions. So that huge number of interactions make them hold tightly with each other. So because of that hydrogen bonding interaction, the cellulose fibers are strongly held, the fiber having great strength here. So this is a normal case. And in cellulose case also, there is another one, like what I explained here until is wood-based cellulose. Okay, so there is another upcoming new cellulose, that is bacterial cellulose. So if you look at the bacteria, so some kind of species, some bacterial species, they are capable of producing cellulose in the culture medium. Like if you grow the bacterial cells in some food like the medium and give some food and allow them to grow, they produce first glucose units and they make the polymerization reaction and produce chains, cellulose chains. Here, this is like the glucose units and chains, elementary fibril, then bundles of fibrils. Finally, you get nanocellulose from bacteria. Okay, so these two are the best examples for top down and bottom up also. Like if you see the plant, you are starting with a wood part, okay, bulk wood part. And from that, we are going down to the nanofibril level. So this is called top-down approach to make nanofibrils. So if you go to the bacterial cellulose, so the bacterial cellulose is like producing from molecules, like producing glucose molecule first, and they combine with each other to produce chain of like polymer chain of cellulose. Then the chains will bind with each other to produce the bundle of fibers. Okay, this is called bottom-up approach. Okay, so this is about the cellulose, and then why it is important. So this is a special properties of nanocellulose. The properties of nanocellulose, there are so many, like I will go one by one. So the first one, it is made up of plant, so it is biodegradable and it is highly biocompatible. Like even you can eat this nanocellulose, nothing will happen to you. So highly biocompatible. So you can use for any application without thinking about toxic. Like so for so many biomedical applications. Okay, and the good thing is they have good mechanical strength. Like the chain, the cellulose chain is very strong. The strength is up to almost higher than stainless steel. They have good mechanical properties and stiffness and the low density. This is also an important property. The cellulose will have very, very less density, like 1.5 grams per kg almost. Sorry, the expression may be wrong. So the cellulose will have lowest density, very lightweight material. Okay, so abundance, and as already explained, there has a lot of hydroxyl groups on the surface. So with this lot of hydroxyl groups, they can be chemically modified. So we already know, like most of the chemistry student will know that hydroxyl is a great functional group for another modification. Like you can bind with acid to make ester, another silane or another functional groups. So you can easily convert into another form. Okay, so as a whole, so the strong mechanical properties and lightweight, okay, and non-toxic and biocompatible nature and high ability to functionalization. Okay, these are the very important properties of nanocellulose. Yeah, let's, so this is a simple scheme, how to make nanocellulose. Okay, a simple scheme. So if you go from wood powder, okay, you start from wood powder. So the wood powder, if you look at it, you can see it is somewhat a brown color one. Okay, so the wood powder is a dark colored one. So it is made up of actually cellulose and hemicellulose and lignin. 3 components will be there. So the lignin is responsible for the color, and the hydrophobic nature of the wood is also originate from lignin. So first we have to remove the lignin. So first this will be alkali treatment. So this alkali treatment at 80 degrees, this will remove the sugar part like hemicellulose. So simple hemicellulose can be removed from this one. Next, the bleaching. So bleaching sodium chloride and state buffer or hydrogen peroxide. The bleaching of lignin will result in the pulp solution. This is white color one. Okay, so if you see the paper industry, pulp industry, so most of them use this kind of process. So you can heard about like kraft pulp or the regular paper pulping industries. They start from wood powder, or if they use a wood powder, they use so many treatments, or if you use some kind of bamboo or some kind of wood, so which is less in lignin content. So the lignin content will be less, so the treatment will be easy. So they treat it, bleaching treatment to produce white pulp. Okay, this pulp suspension can be used for several applications like paper making, packaging, and other things. But this is just composed of cellulose, but there is no nano-sized cellulose. So next we have to make the nano-sized cellulose from this pulp solution. Then there are 2 types of techniques. So the first one is mechanical treatment and the second one is chemical treatment. So the mechanical treatment or defibrillation. So this will like mostly homogenizer or another big machines will be used here. So they will apply high pressure on the pulp solution. So due to the application of high pressure, the solution, I'll show you. The fibrils part will get separated, the fibrils. So the fibrils will get separated into fibers. I can say this one. Yeah, this is some representative images of cellulose nanofibrils. So if you see, this is the microscopic images of cellulose nanofibrils. So you can see the structures. Like here, if you see, this one is thick fibers. The size is looking thicker. So if you keep on treating, like strong mechanical force, if you apply, so this will disintegrate to small, thin fibers. Okay, these are different types of fibers. This structure will be, so this is looking thin fiber-like structure. And this cellulose nanofibrils having the advantage of, like they are very long fibers, so their thickness and length. So the ratio is called aspect ratio. Higher aspect ratio will be there, means the length to thickness ratio is very high. So because of that, they look like a fibrous network-like structure. So this network-like structure they make film-like structure, hydrogels and aerogels can be formed with this one. And a second treatment is acid hydrolysis. So this is simple one compared to mechanical one. So here you apply strong acid to this pulp solution. So the strong acid like sulfuric acid. So this acid will react with the pulp and it break down all the amorphous parts. So like I already explained here. Yeah, here if you see. So this is the fibrous part. So the pulp fibers look like this. And if you apply strong acid, so the strong acid will dissolve all these amorphous regions. So it will break down here and dissolve all the amorphous region. So this remain only crystalline part. So compared to crystalline part, so amorphous is little weak and easy to digest. So because of the strong acid, the amorphous part will get dissolved in the acid. The crystalline part will remain there. So then we separate them by using some dialysis and other techniques, and you get this kind of nanocrystals. Yeah, this is some representative images of cellulose nanocrystals. So this rod-like structure, thin and rod-like structure, they are highly crystalline in nature. So due to their high crystallinity, they are very strong, and they can be used as reinforcement for other plastic materials. Okay, like they improve the mechanical properties, tensile strength of other plastic material. So applications of nanocellulose. So here, I will simply explain this. So the application part. So you already know about the pulp or paper. So the pulp or paper is also made up of cellulose, but that is not nano one. So the paper cardboard industry. So the paper or pulp packaging material. So they are reinforced with the nano one. Like what I can say. So the majority of the pulp will be there, 90%, but 5 to 10% nano-sized cellulose or nanocrystals or nanofibers will be sometimes coated on it or reinforced on it. Okay, inside fill with that one. So this will improve the mechanical properties of the regular packaging material. Okay, the packaging like all the things. So, and other thing goes to catalytic membranes. So with the mesh-like or entangled fiber-like structure, the cellulose nanofibrils can form a good membrane-like thing. So if you properly make that cellulose nanofibrils, like by controlling its chemical functional group, so that they will offer different surfaces, like highly negative charged cellulose nanofibrils you can make. So that highly negative charged one, then if you make it a membrane, so it will absorb highly positive charged ones. So like that, it can be used for pollutants absorption. Or catalytic membranes means if you bind with them with another material, like another catalytic material, if you deposit that one on the nanocellulose, like cellulose nanorod, and deposited with another metal nanoparticle, so that it will serve as catalytic membrane. Because this is nanocellulose mostly act as a support for another material with its lightweight and high mechanical property. So they serve as a good support. So for many more materials like metal nanoparticles, carbon nanoparticles, for all these things, these act as a support. Okay, and when they mix with that active ingredient like active nanomaterial, they can be used for catalytic and energy conversion, like another sensing device. Okay, biomedical applications like water purifier or air purifiers, all this it can be used. And biomedical field. So as I already told you, like the cellulose will be least toxic, like almost non-toxic. But if you make them from strong acid, and if some kind of acidic or other functional groups are remained on them, then they will have little toxicity. But most of them are non-toxic, so they can be easily used for biomedical applications. And most of them are already commercialized. Some things like whatever the band-aid you use, like wound dressing thing, when you use that, are mostly made up of cellulose. And biomedical field, the dialysis membrane, what are the membrane is made up of cellulose acetate and most of them. And pharmaceutical industry, all like the inactive fillers will be made up of cellulose because they are non-toxic. So the capsules can be manufactured with cellulose and their composites. And in cosmetic industry, like beauty products, like the cellulose, another important property of the cellulose is they are highly hydrophilic. So the nanocellulose is highly hydrophilic. It can hold a lot of moisture. So it will be added to the cosmetics. So where it can hold a lot of moisture and the other substance, cosmetic substance. Okay. Okay, so these are the applications and some are already in use. So you can find in everyday life. Some like paper and packaging, all the things are already being used. Last, coming to the limitations. So why it is not replacing plastic yet? Okay, you can have the question like it is saying the sustainable replacement for plastic, but it is not real. Why? There are some limitations. So the major limitations I noted here, like the high energy is required for defibrillation. So the making of nanocellulose required high energy input. So it is not commercially not viable, like not viable over the regular plastic because the regular plastic is very cheap. So compared to the cheap, the nanocellulose is still little more expensive. Okay, one. And the second one, the hydrophilic nature. So nanocellulose, you already saw so many hydroxyl groups are there. So it can form many more hydrogen bonds. So it will be bind with moisture, like it will hold a lot of moisture. So the drying is highly difficult. And if you dry also, it will become aggregated. Like drying result in massive aggregation. So aggregation means again, it loses its nano nature. The fibril become bind with each other and come close and forms a big bulk material again. So if nano nature is lost, then there will be no advanced properties. It will become pulp. And if you want to remain the nano nature, it should not be dried. It should be in the wet condition for the better, better getting their properties and better using. So if you want to keep it in nano state and get most out of it, you need to make it a wet form. But the problem with the wet form is transportation. So wet material will be very high. Like 1% means like 1 gram cellulose in wet condition will be 100 gram weight. So 100 gram weight transportation is not economical. So these are some limitations. But the research is focused on these things, addressing these challenges. And I'm very sure that in near future, the plastic will be completely replaced with this kind of nanocellulose. So thank you. So anyone have any question? Or?
Okay. It is the discussion time. If you have any queries, you can raise your hands and speak freely.
Yeah, I'm very happy to answer you.
Yeah. You can also post your questions in chat box also.
Yeah, that is good.
That is good, yes. Yeah.
Yeah. Maybe we can have some discussion. They will come.
Yeah, it is the very newest topic to them.
Yeah.
Students. That's why.
So I think you can raise a little questions like you know their curriculum and everything, sir. So you can.
My question is Rajkumar.
Yes, sir.
Actually, most of the cellulose particles are have already explained. Most of them OH groups attached, poly OH groups are there. Whenever we are utilizing this as a replacement to the plastic. Is it
Yes.
it is any chance to soluble in water? Because the plastics
No.
are very
Yeah,
insoluble.
very, very good question, sir. I am sorry I forgot this. So
Yeah.
cellulose is highly like hydrophilic, but insoluble in water.
Yes.
Insoluble, it will swell a little. If you add more water for a long time, it will become little swelling.
Yeah,
But
exactly,
it will
wood
not dissolve.
properties of wood.
Yeah, just like yes, swell, polymer property, it will swell, but nothing. So, and most of as of now, the research is like not completely replacing plastic with cellulose, but they
Yes.
use biodegradable another plastics like PVA, something biodegradable, PLA,
Yes.
polylactic acid, some bio-based plastics, and they are adding cellulose to that. So the cellulose with the high strength, so it acts as a, sorry, I can stop sharing this one.
Okay.
Wait, sir.
Yeah.
I think I'll stop.
Can I summarize? Is there any questions,
Wait.
please?
Let me like.
Feel free to ask, please.
So they are looking at the slide or me?
Yeah.
Thank you, sir. Thank you for giving such a valuable webinar.
Raviteja, you open your video. Yeah.
Sir, good afternoon, sir.
Yes. Very thank you, Rajkumar. It's a very excellent
Someone
lecture.
is asking. Someone is asking, sir.
Construction of cellulose, how the
I think someone is
nanocellulose
asking.
are naturally constructed with the bacterial cells and plants, right? And also explain the synthesis pathways and explain the properties, and very interesting applications are also very. It's very much interesting and thought-provoking lecture. I think it is very extraordinary lecture. Okay. Yes, it's the time to vote of thanks. First of all, I thank our beloved Vice Chancellor and Registrar and administration for giving required approvals for conducting this kind of extension lectures and online webinar programs. Okay. Now, and also we also thank our Director Academic, Dean Faculty of Science for constant encouragement towards to conduct this kind of lectures. Okay, and my special thanks and on behalf of department and faculty, we are always thankful to Rajkumar for accepting our invitation, even though our former colleague. We are very much happy for giving this lecture, and also I thank all the participants and supporting staff, computer center, AVPRC. Thank you very much. Thank you.
Yeah, can I last? So thank you. I need to say thank you, I think.
Okay.
So thank you. Yeah, thank you for like it's like coming
dear
back
participants,
to my home.
Please fill the Google form. Attendance form is already posted in chat box. Please open the Google form, fill it for the attendance and for other proceedings.
Yeah.
Thank you.
So thank you. Let me share. Thank you. Thank you to the head department and dean, all madam, and thank you, madam. Okay. So this is like after a long time, I come back to the university, even though I cannot physically come back to the university. Just I am online at least. So I'm happy to like serve the university again after this long time. So I wish all the best to the department and our new students. Okay. So I can be if anyone have any question, like I will be ready to answer, and you can share my number, mail, or anything, sir, to our students.
Sure.
Sure. Thank you, sir. Thank you.
ముసురుడికి అర్థం అవట్లేదు కదా, ఈ ముసురుడు ఏం కాపట్లే. ఫ్యాన్ ముసురుడా నేను మాట్లాడింది వినిపిస్తుందిరా ముసురుడులే.
Please leave. Those who are filled the Google form, please leave. మీరు గూగుల్ ఫామ్ ఫిల్ చేసేటట్లయితే మీరు దీని నుంచి బయటకు వెళ్ళొచ్చు, క్లోజ్ చేసుకోవచ్చు మీరు. థ్యాంక్ యూ. Do you have any doubts for filling the Google form? You can ask me free. If you have any doubts, you can ask me during the filling the form. If you fill the form, please leave the session.
Sir, good afternoon.
చెప్పేసి.
Sir, department designation, organization, Bravo, we have to write up.
1 hour కదా, మనం 11:30కి ఎగ్జాక్ట్ స్టార్ట్ చేసి ఈరోజు ఏం లేట్ కాలే, ఎగ్జాక్ట్ 11:30కి స్టార్ట్ చేసి. మంచి స్టఫ్ ఉంది మేడం. మేడం లేదు లేదు, గూగుల్ ఫామ్ ఫిల్ చేస్తున్నారు, అన్న డౌట్స్ ఉంటే ఓపెన్ చేసి పెట్టి ఫీడ్బ్యాక్ ఫామ్ మేడం. తక్కువే, జస్ట్ వాళ్ళు ఇన్ఫర్మేషన్ తీసుకుంటూ 2-3 క్వశ్చన్స్ అంతే సెషన్స్. మీకేమన్నా అంటే ఏం క్వశ్చన్స్, మీకు నాలెడ్జబులా లేదా?
Hello. Sir, good afternoon. Hello. 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 Hello.